Hello, everyone. Welcome to today's webinar covering ADAPTBuilder. Today, we're going to be talking about just some basics of post-tensioned. This is mainly two-way slab design, gravity design, and ADAPT, specifically ADAPT Floor Pro. And we've had a couple of webinars previous to this that covered just some basics of RC design. This one will be similar in nature, but today we're going to focus, I think, a little more on the design of the post-tensioning serviceability requirements for the slab itself, and we won't focus as much on the modeling. So we're going to record today's webinar, and that will be put on our webinars playlist at youtube.com/adaptsupport. You can go back and play that back at any time. Today's webinar will last roughly an hour. We'll have a short Q&A session at the end. If you have more detailed questions that we're unable to get to, you can always contact us and email support@adaptsoft.com, and we'd be happy to give you a hand there and provide more detailed information. For some of you, I know this is likely going to be fairly basic, but we want to make sure that those that are new to the software and maybe using it for the first time, that they're able to understand some of the basics and just the fundamentals of how the program operates and how we would go about analyzing this post-tension slab. So the model that we're going to be using today is going to be, this is actually the same model we used for the RC structure, but we're going to go ahead and just take a level in the upper few floors here as the PT example. So it's a pretty basic model, but it will show the general process and workflows and being able to add the post-tensioning, go through some design checks, and then also using the tendon optimizer inside of Builder. So let's go ahead and get started. By the way, my name is Spencer Lee. Many of you, I may have talked to you in support, and again, I appreciate everyone's attendance. So let's go to Analyze. We're going to go ahead and we're going to export this file out through use of the Adapt Revit link. We won't spend too much time covering this. This was covered in the previous webinar. So let's go back and just save this IMP file. This is the generic Adapt Exchange file that we're going to be using, mainly for integration with other programs, just third-party programs, and also within Builder itself. If you have a multi-story structure and you want another person in the office or maybe at home now to be working on a specific level for PT design, you can always export that level out using IMP, and then you can go through the design of that single level. There is one question. Let me go ahead and ask this. The question is, will there be an update for our integration console to ETABS 2018? Yes, there will be an update. I don't know when that update will occur, but right now I think the primary focus is to improve some of the core features and capabilities of Adapt Builder itself. So that kind of displaces some of the resources available to work on other items, but that is an important tool that we have, and yeah, we will get to that, Marcus, but it just hasn't happened yet. So let's go over here to Builder. Today I'll be using Builder 2019. This is actually build 2. This will be released quite soon, but you may see a few differences. I'll try to explain those as you see them. So we're going to make sure that our primary program we're going to be using today is Floor Pro. We won't be using Edge. We're not going to be modeling, or excuse me, analyzing the structure in multi-story mode, but we'll go ahead and just leave that on for now. It can be left on, just not utilized. And then we want to make sure we have the PT RC option turned on for production of the post-tensioning. Also, I'm going to turn this felt shop, PT shop / felt 3D option on. I'll kind of show you a few things related to that. It's not as common to use these two features when you're not producing shop drawings, but it may be useful if you wanted to actually use the program's capabilities to calculate the long-term and the short-term losses and elongations for the cables, rather than just assuming an effective force for the design. So if you're in a situation where maybe your elongation reports come in short and you assume some effective force, and now you need to sharpen your pencil and determine really what are the actual losses that we're getting. Maybe you want to check those against the PT shop calculations, then you could use this tool. So we'll have that on kind of in our back pocket to use. You'll notice something up and coming here is going to be this property grid. So this will allow you to make changes to components more quickly, and it's just an easier way to make changes other than the old kind of legacy modify selection option where you had to go through a few clicks to get to that point. So this is going to be a nice new feature that will be up and coming here very soon. So let's go ahead and import that file. I'm going to import that IMP file that we had created. Okay, we're going to import the entire model. There are no load cases or combinations. We'll just go ahead and import everything, but we're primarily going to be working in single level mode. So right now you see we have a multi-story model. I'll go over here and I'm going to go up to the 6th level, single level, and we're going to primarily be working on this level. Now this slab is a 9-inch slab. I'm actually going to change it to 8. I think it was sized originally for RC. We're going to change that to an 8-inch slab. And we're going to just jump right into loading the model with some gravity load and then getting into design strip layout and tendon layout. So let's select the slab and we're going to go over here to loading. I'm going to just map loads to the slab outline using the wizard feature. The 2 load cases that are reserved load cases, they're just essentially the default gravity cases, are the dead load. This is going to be superimposed dead load and also live load. It's important to, before you actually start adding load and defining it as this particular dead load case, I'll make one comment about load balancing. So if once we kind of get downstream into the presentation, we're going to have design strips set up, and in each design strip we're going to define a span. So you're going to have, for example, a point here at this column, maybe a point at that wall, a point there, and a point here. And the program, this is span 1, 2, span 3. And when we add post-tensioning in the slab, then the program is triggered to generate the solution, for example, for load balancing percentage. And when you check that, it's going to give you a percentage here. Maybe it says, 50%. And that 50% is a function of the self weight and the reserved dead load. So if you want the program to check load balancing based only on self weight rather than and simply ignore the dead load, what you're going to want to do is disassociate any load from that reserved dead load case. So in our case, we would come over here to load cases and say, well, I don't want to use this dead load case because of that. I'm going to add a new case, and this is easy enough. We'll just call this SDL, and all of our load cases, or all of our loads would rather, they would be applied to this SDL versus this dead load case. That will require an update in the default load combinations, which are all kind of set up towards that that dead load case. So you would have to come in and modify these factors, or if you're using a template file, that template file may already include factors that are associated with this new load case that you write into this dialog. So a template file, if I started a new model and I went ahead and said new, create a new file, I could select a template file which stores material. I think I'm good there. I thought I deleted that or overwrote that. So so that's one method. Another method is just to import load combinations from IMP. So if we have 50 combinations that we're using over and over and over again, rather than wanting to come in here and rewrite them, I doubt any of you want to do that and waste time doing that. So we could always go to File, Import, IMP, and then we could actually just import the load combinations from an already existing file that includes them. So there's a couple of ways around that. We're going to use just everything kind of default today, just for the sake of time, but I wanted to bring that up and mention that as we look at these loads. So let's come back here. I'm going to bump up the live load to something probably unorthodox. So I'll use 80 PSF live load. I don't think that's listed anywhere in the IBC live load tables, but it might be. I haven't checked that recently. So let's go to live load, and we'll say we're going to use 80 PSF live load, not 800, but 80. So we'll do that. And the loading, just very quickly, visibility wise, it's hard to see that, you know, in this view unless you come over here to the loading visibility panel, and we can go ahead and turn on, for example, the dimension of the loads, and then we can see, you know, those two loads are added and toggle between them, selecting that. From this perspective, we can see the loads clearly. If you don't like the height of that load symbol, we can change that, just change the symbol size here for the patch load. Patch load is the same as uniform load or distributed load in the model. So we have some loading there. The live load itself, in this case, is going to be unreduced. So during the last training with RC, I discussed how loads are reduced for floors in ADAPT. So I won't spend time here in this presentation going through that, but it involves the use of subregions where you have to set up a load pattern that then would automatically be used to reduce the live load on the floor. In this case, we'll just assume we're using full live load for this example. So let's go ahead now and go to material properties for concrete. We're going to select criteria. Under concrete, I'm going to go ahead and change this first concrete to 5,000 PSI. That's pretty common for two-way plates or two-way slabs, post-tensioned. And we'll just say that all of the columns and walls are also set to the same concrete. There's a question. Quick question on live load reduction. Can they overlap, or we need to keep them separated? Pavel, I don't know if you're referring to the actual subregions overlapping or the loads themselves, like having the loads. Yeah. So yeah, the loading can overlap. It's just if they do overlap and you have a subregion that has two loads, you know, in that subregion, then both loads would be included being applied in the subregion. But you can only assign one load to be patterned. So yeah, issue where was, yeah, I would have to go back, Pavel. I know you're referencing an issue that was back in 2018. I would just need to go back and check some history on that. It doesn't come to the top of my head in terms of what we've done for that particular issue in version 19. So I can contact you after the webinar and touch base on that if that's okay. All right. Let's go back to the layout of strips. Now, the post-tensioning is in this program, it's flexible, meaning it's really customizable by the user. How do you want to lay the post-tensioning out? There are replication tools, and there are ways to go through and more easily adjust and modify the cables, but at some point you have to enter those cables into the slab. So we first have to determine, okay, which way are we going to use for banded cables, which way are we going to use for the distributed cables. Technically, if you wanted to, you could say, well, I'm just going to represent both directions in the program. Remember, it's just a model used to simulate the slab. So you could then take the information from the model and portray it however you want in your drawings, as long as it's compatible with the actual solution. So in this case, we're going to say that the Y direction is the banded tendon direction. So we're going to have tendons that do something like this. This tendon, I'm going to say, will just split. We'll have a tendon here and a banded tendon here. And then I'll represent the distributed tendons in pink. Now, again, if I wanted to represent the distributed tendons as let's say bands, then I might say, okay, there's a bundle here. There's going to be a bundle along here. Remember, the blue tendons are banded, so they're really like virtual beams in the slab that carry the distributed tendons. I might have another distributed cable here. This one might swerve up and do something like that. So these might be, this might be represented as a banded system. Some slabs are more conducive to doing this type of an approach. For this slab, I'm actually going to represent all of my distributed cables as 4-foot groups of cables every 4 feet. So if I have a 4-foot section here, this is 48 inches, 8 inches, and I say I want to target at least 125 PSI pre-compression for this unit section, I want to have at least, you know, by calculation, we need 1.7 some inches or cables per 48 inches. You can actually enter that into the program. You could have a cable that's in decimal format. It's not a whole number. So, but I'm going to round up. I'm going to have a little more pre-compression. I'm going to say every 4 feet, we want two tendons every 4 feet. So that will be my uniform cable direction. For the banded direction, I'm going to utilize tendon mapping in the program. And so to map tendons, I have to have design strips laid out to begin with. So we're going to go through, before we actually add the post-tensioning, I want to generate my design strips. Let me go ahead and turn off the loading here. And we're going to add the X direction strips and the Y direction. I'll start with the Y direction. The Y direction strips, I typically will lay those out such that they are, they kind of follow the same path as the banded cables. I want my tendon to intersect the design cuts, the design sections, at a 90-degree angle. I don't want to depart too much from that angle. In other words, I do not want a design cut here and then having a banded tendon cutting at it like this, where this angle is, say, 30 degrees. That is not a good way to model the tendons with relation to the design cuts. So what happens is you might have another cut. I'll draw this in yellow. You might have a cut belonging to a X direction support line here for this yellow cut, and that banded cable really is going to affect the results essentially in both directions, where its really primary purpose is really to be maybe in affecting the results for strips in just one direction. So we're going to go ahead and select Y support line. Notice if you're an old user of ADAPT and we've brainwashed you into selecting or starting the support line at the slab edge, in the new versions of the program, you're no longer really required to do that. So you'll see I'm violating all these rules that we've set up over the last several years. So hopefully that's been an improvement for some of you that have used the new versions, but you'll see I'm just really snapping on the column. I'm not actually snapping down on the slab edge. You could still go to the slab edge or beyond. It's a little more forgiving now. Okay, I turn on this snap to nearest just so I can snap somewhere along the center line of that wall, and I'll turn that back off. It can be a little bit difficult to work with if it's left off or on. I'm also going to or if it's left on, I'm also going to generate a splitter. I don't want the cuts to actually extend into this boundary. Okay, technically it doesn't really matter from the standpoint of designing or processing the solution for the sections. There was one issue where if a section cut into an opening and you actually had like a rebar mesh, the program would actually utilize that mesh if it was mapped over the slab where you had an opening. So that would be a case where you wanted to bound this off. That has been fixed. That's no longer a problem, but just from a historical perspective, there was, one side effect of having that cut into there. So I'll now use a Y direction splitter. These are Y support lines, so I'm using a Y splitter, and I'll just add that splitter to those two edges. And now you'll see if I generate the cuts, these are my design strips I'll be working with. We have a little bit of overlap in a few spots. If I want to clean this overlap up right here, I could just run another splitter, just there and run it out of the slab. It's fairly forgiving in terms of how you can use these splitters. So I'll add another one there, and maybe another one, there. And if I regenerate, there's a little bit of overlapping between these two, so I'll do one more along there. Okay, and these are my strips for this direction. Now I could go through and model now the X direction strips. Let's do that, and then I'll come back to these and use it to do the tendon modeling. So I'm going to go and to control the visibility of this, I can use this visibility panel for strips, and I'll just turn off my strips and my splitters that I've added. So both directions are completely unique. They're not using any information that you've used for the other direction. So we're going to go ahead and add X strips. Now for the X strips, remember I don't necessarily have to be on a actual support when I generate the points on the support line. Remember, the banded tendons are really the supports for the uniform cables. If I was modeling this in ADAPTPT, which is really just a 2D equivalent frame program, then I would have to determine, how should the strip be laid out. So for example, if I wanted to break this slab into 2D strips for that program, I might actually take this and go up to this column, over to this column, down and over. That would be strip 1. Strip 2 might be this area here. We're going to assume this is ignored. That's just too short to pull a tendon. The other strip might go from here up to this wall and swerve down. So these would be my idealized, let's say, geometries if I was using ADAPT-PTRC. This would be tributary, 1, I guess that's 2, I said it was 2. This would be 1 here. This would be 3, and we might cut this out, and then 4. And so here we're kind of swerving to supports, but in ADAPTBuilder, I'm trying to keep my support lines, let's say, orthogonal or in the same direction as my uniform cables. In this case, the X direction. So we want everything to be aligned in that direction. So let's go ahead and do that. I'll add a support line along this path. I'm gonna start out of the slab here. The reason I start out of the slab is just easier than to go down here and select snap nearest, zoom in, try to snap on that slab edge, zoom back out. So it's just easy to start and then come back and adjust as needed. So we'll do something like that. I'll jump down here. And then finally, the last one will be here at the bottom. We might have, a couple, it would be just to the discretion of the user. We actually might want to do one there and then along this line, but I'm going to leave those out for now. Okay, so these are our strips in the X direction. And the more strips you have, the more design cuts you're going to have, which means you're going to just have more, of a refined breakout of results in the slab per the strip method. You'll be able to just, refine the number of design points or data cuts rather for that. So again, in this direction, we're going to use an X splitter, and I'll bound this opening off from the design cuts entering that area. And I'll generate my strips again. Okay, so this is the generation of the design cuts. This looks a little strange with this clustering of all these cuts. We can try to get away from that, entering that wall space if we were to just bring that splitter maybe outside of the wall boundary. So we'll just drag those out a bit, regenerate under floor design, just regenerate the design cuts. That's probably as clean as we're gonna get for now on this. This one, you can see this section right there, that could be detrimental, especially if this is a banded direction. and you have one section that's quite a bit longer than the other sections because the program uses the section geometry to determine the force that it maps. So in this case, you know, this section here, there's this cutout in the slab, so this roughly is equal or less than these larger sections. So it's not a big issue here, but if we wanted to resolve that and revise that, we could say, well, just take this over to the edge, and that would then, you know, because that point is at the same position as this point, now this doesn't extend over because this one was previously scooted to the left. Or you could use a splitter there also. So the point locations is important to note those and determine, you know, how that might be affecting the different section cuts. All right, so we have our strips in the X and the Y directions. Let's go ahead and map some tendons here to this banded line. So we're going to go over to tendon. Actually, before we do that criteria, make sure you check your pre-stressing material. We're going to be using 1/2 inch unbonded, just monostrand, so coated monostrand material, just kind of typical stuff you'd see in a 2-way flat slab like this. Again, these are going to be unbonded, and so we're going to go over here to tendon. Before I actually start mapping the tendons, we want to make sure that the tendon height is set properly. So for when the program maps the tendon, it's going to use these values to position the tendon. So if we have our slab here, and let's say here's a support, and then you know, we have midspan. Let's say midspan is at this location. I'll just put an arrow there. The tendon's going to drape over the support, and then it's going to drape down low here. So this CG from bottom of slab up is 1 inch. There's the bottom, and then 1 inch from top. That's to the center of gravity of the cable, or the steel of the cable. And so once we position that, the program will never move this down to meet the balanced loading when we map tendons. It never moves the high point down, it always moves the low point up. So this tendon could be moved up incrementally depending on the target load balancing for that span. So just make sure you have these set up proper before you map, otherwise you're going to have to go back and likely change the points for your cables. All right, let's do this. I'll take this as an example. We're going to go to the option under tendon, and we're going to map banded tendons. Now, if you're really experienced or really good at post-tension design, you can always just go in and draw your tendons. You don't have to use mapping. You could just say, well, I know for this thick of a slab and these span lengths, I need 10 tendons exterior, maybe 15 interior, and you could just draw them in and then manipulate and modify them as needed. We're going to use the tool here for mapping. So I'll use the design strip width. The program will actually determine what's required to meet the geometry of the strip in terms of force. So we're going to target pre-compression, minimum pre-compression, and maximum pre-compression. I'll change this to 300. And then load balancing, I'm just going to balance 50 to 100% of self-weight. So the placement is something that users all have their own feel and the way they like to place the tendons. If I needed, in order to meet these two targets, if this strip required 10 strands, I could say map all strands and just space them at 1/2 foot. Okay, and what will happen is the program will say place 5 on this side and 5 on this side. So there's no logic there that says, well, this is an exterior support line, put all 10 over on this side. So you have to do some post editing and manipulation. I'll just give you an example. Okay, so do you see some of the tendons are actually out of the slab, and this said we needed 7 strands to meet those targets for this strip. Well, I don't want to manipulate all of those tendons, and I don't want to have to manage maybe all of those tendons. The more refined you get with the tendon placement, the more accuracy you're going to get with just the raw FEM results. So for example, deflections, though a lot of times you're going to evaluate deflection based on the finite element 3D contour maps versus the strip results. So if you have a really sensitive issue with deflection, you might want to go to modeling every tendon as it truly is spaced. That might be more of an investigative type procedure versus just a design or a preliminary design procedure. And when you're just doing preliminary design or just, maybe even DD level type design and you don't have those issues to deal with, then we go into mapping banded tendons based on maybe an idolization of the tendons. And by default, I think just from a legacy standpoint, we've always kind of used two tendons straddling one side of the support line. And on exterior spans, you might have just one tendon. So we're gonna use two tendons. We're gonna use 1 foot apart. I just simply like to balance the discretization of the force on both sides of the support line. So when the tendon is modeled, it actually gets chunked out into sections or segments, and it's really dependent, the solution gets dependent on the discretization of the segment and also the refinement or lack of refinement of the shells. So you could have shells every 10 feet. That's probably too gross of a spacing for your shell elements. You might want to mesh it down to no more than say 3 to 4 times the thickness of the slab for a good mesh. So here we're going to say space them on either side 1 foot. We're going to assume a force in the cable. So for a 1/2 inch cable that's unbonded, we might say the force after all losses might be 26 to 27 kips. This is 26.7. ADAPT has historically used an effective stress of 175 KSI. So after you apply just the jacking ratio, which might be 0.8 FPU, you get down to about 216 KSI, and you take out then the short and long-term losses. That's roughly about 40 to 45 KSI. That gets you down to 175. So you could assume whatever you'd like here. This is just, again, the default. The shape of the span, first span, mid span, last span. So that the wording there can be tricky. This might indicate, well, that's only 3 spans, but this first span literally means the first span. So if I started down at here, this is point 1, 2, 3, and 4. This is span 1. This is mid span and span, last span, or I'll call this first span. If you had more than 1 span, then everything in between last and first will be mid span. So I wouldn't get too hung up on the shapes. Where this might get a little tricky is where you have a situation when you're kind of following the procedures that you've learned over time, and you have a column. I'll kind of blow this up here. You have a column and a slab edge, and you have a support line that runs through here, and you actually put a point there, but then you put a point there. This is technically a span, and so is this tiny distance. And so when you map the cable to this, it maps it to the spans. So you're going to have a reverse parabola in this span and a reverse parabola in this span, and that's just not going to happen. Or you wouldn't want to use that for that tiny span. Really, the cable, if I flatten it out, the drawing of it, the cable here, might be low, and then it would just kind of exit out of the slab at the CG here. So you'll have to go back and kind of edit that after you've mapped. That's something that's pretty common if you're creating those 2 points, which in the past was, a legitimate requirement if you didn't want to add a bunch of splitters to generate the design tributaries. So keep that in mind. Let's just use this as the default. The X1, X2, X3, those are just the inflection points as a function of the span length. X2 over L, that typically wouldn't change in our uniform loading condition unless you're trying to shift the efficiency of the cable based on like a moment diagram. It might be something that you do in practice, but we'll just leave those as 0.5 and we'll map that. So again, notice here that the program actually does throw that cable out of the slab. We can just go through and manipulate that and move it into the slab. So I'm just gonna grab those points, move those inside the slab. Don't worry about this gap yet. We're gonna take these tendons, and I'll actually do this for all of them at once we model the rest of them, but we can take that and use the trim extend feature, and that pushes the cables out to the slab. And let's move this cable. I'm gonna move that cable down to somewhere down here. Okay, if you want to shape the cable other than being a linearized cable, meaning straight segments between high points, the way the tendons are represented in the slab, let me turn off the strips. Excuse me, the blue points are low points. So this is a low point. The color red, or the same color as the cable, that's a high point. If you want that symbol to be larger, you can control that under visibility view settings. It's what we informally refer to as the blue eye glasses. It's also down there on the bottom. And the anchorage is also the same color as the tendon. Now, if you go to a spline tendon, if I double click on this tendon, and one thing to note, a new feature upcoming, if you go to stressing, in the past, you could wreak havoc on your design when you design reinforcement. For example, as a user, if you enter one cable, if you go here and say, well, I'm just going to use one cable, but I'm going to enter a force of 500 kips, and you don't adjust the area of the cable, you would get some really strange results for reinforcement and capacity. The program will have a new feature that allows you to lump sum the total force here. You just select that and then enter the lump sum value, and it would actually scale up the number of strands based on whatever you enter here. So that's a new thing coming. But if we go to the general tab and we say, well, change this to spline, we have a corner right there. I want to show the curvature of this cable around that corner. And using a spline, you can see that curves that cable, but you also have kind of this back span that also has to maintain its shape relative to the shape function used for the spline. So sometimes that's not really realistic in terms of how the cable would be truly laid out in a shop when we're producing shop drawings. So another option would be to use the fillet with a radius, and that option allows you to keep these tendons essentially linearized, and then where it turns, you have some radius here where that point is right there, and then on the opposite side right here. So this is kind of an in-between linear and spline, and both the fillet and the spline options, they will produce a separate color for the high point. You can see this is like magenta versus red. There's also a swerve point. So if you wanted to move that cable and swerve it, here, then you could adjust the curvature of the cable by using these swerve points. And you could always add a swerve point to a span. So if I was to take this back to spline and say, well, I don't want that to kick out this direction, I could just right click, or I could go to modify, or excuse me, the tendon tab, and we could insert a swerve point, maybe like so, to straighten that out. And then I can control the in-plane sweep of the cable just using those points. That doesn't control the high or low point. Those are fixed based on this location here and this blue point. Notice spline, it's green, fillet, it's magenta, linearized, it's red. Low points are always blue. Okay. If you go to tendon display manager, okay, you could also turn on the inflection points. Those are shown as gray. So there's a lot of data you could show on the cables when you're displaying these graphically. All right, so let's go through, and I'll leave those as they are. I'm going to go back to floor design. I'm actually going to map all of my tendons at once here. So let's just take all of these, go back to tendon. I'm going to use the same parameters for mapping, so the same Same things here, I'll just say, okay, this maps all of my tendons. And you can see all of them because I changed this to spline. The program carries that same setting over to the additional tendons before, unless I changed it back. So I'll just use these cables. I'm actually going to linearize the cables. I'm going to go back and just select. I could also just select by type, tendon, and we can modify the tendon under, let's go to modify selection. This is the old way of doing it. The property grid will be the new way of doing it, but we're going to use this option here. And I think, I'm not even sure if that should be in here. I don't see it though. So let's go back out. I'm going to actually delete all of my cables. Yeah, let me delete these cables here. The nice thing about mapping is it's pretty quick. It just, the time is taken when you're editing, editing the cables. This one is already linearized. I'll just leave that one alone. I'll delete the one outside, and maybe this is a case where you use only one strand, but when I delete it, I have to remember to go and bump this up by a factor of 2 because I had represented it as 2 cables. You can see the shape of the cables there. So I'm going to come back to this cable right here. I'll turn this back to straight line. That setting would then carry over when I map the additional tendons. And let's go back and map those one more time. Okay. And then these cables turn pink when they go through an opening. In previous versions, that would not happen. It would only turn pink if it was outside of the slab. In the new version 2019, it will actually flag it and give you a warning even through openings. So that's a little bit of a change there for those of you who are using the software more often. Now I'll just select all cables, trim and extend. That pushes them out to the slab edge, and for this exercise we'll be done with the tendon mapping. This may not be exactly how we lay out. This area down here is a little bit strange, but we'll leave it as is for that. So those are our tendons. One thing I recommend you do is after you've mapped tendons or modeled one direction, just go into the visibility render model option, just a solid modeling tool. I'll turn on the wireframe. I'm going to turn off columns and walls, and then I can factor up the Z direction, and we can kind of see the shape of the cables. So this will help pick up any points where we might have, really drastic curvature in a cable. For example, I mentioned that at an endpoint, if you have a tiny span, you might have that reverse parabola. Sometimes you miss that. And so this is a nice way to catch those areas. And one thing to note is the program picked up the walls. There's actually a wall here and a wall here. The tendon drapes down and it runs straight over the wall, and then you get back into a reverse parabolic shape on the 2 exterior spans. So that was picked up automatically by the program. Let's go back. Those look okay. And now we're going to run with the distributed cables. With the distributed cables, I'm going to use, I'm going to turn back on my banded tendons, but I'm using them mainly as a reference to develop what I'll call the primary tendons that can then be replicated. So we're going to add a tendon, and I'll start here. I'm going to say that my tendons, for every 4 feet, I need 2 cables, okay? And that was calculated if I just take the area of a unit strip. It could be 1 foot, it could be 2 feet, 3 feet, whatever you determine as the unit spacing of the cable. That's really your decision. The code, the ACI code says they have to be spaced no more than 8 times the slab thickness, so that might be a limit, but here we'll just say every 4 feet. So this cable, we're going to say we need 2 cables every 4 feet, 2 tendons. Let me see if there's a question here. Okay, nope, no question. If you do have a question, feel free to, there's a question box in the GoToMeeting portal. You can go ahead and ask questions there. So this cable, the profile of the cable will be set under shape system friction. We're going to just simply max out the drape here You know, as you get more and more experience with post-tensioning, for shorter spans, obviously you may not need as much drape, so we could go through and adjust those as needed. I actually like to just max out the drapes, then go through and adjust tendons using the tendon editor tool. And I'll show you that here in a moment. Make sure your control points are set properly. The stressing, we're going to say this is 26.7 kips. You could also calculate the force. So if you actually wanted to dictate where the live and dead ends are for the tendons, you can set those here under calculated force. You have to assume your seating loss, then how is the stress going to be delivered? Is it going to be based on a jacking ratio, a force given, or a stress given? And then you also have the option to estimate or calculate long-term losses for the cables. So there's several different things you can do here. If you just want to say, well, I'm just going to predict that, you know, I'm not going to use a varying force. I'm just going to say the average force in the cable is 26.7. That's fine. We'll do that. And the next thing we'll do is copy this. So I said every 4 feet I need 2 tendons. So I'll go to modify. I'm going to copy this down. We'll copy it down 12 times. Before I start modifying, you'll see this banded tendon starts to swerve inward, and these points are starting to diverge away from the center of those bands. So one new feature that we're going to add is automatically adjusting these intersection points, but for now it's really left up to the user, if you do replication like I'm doing, to come back and modify these. You don't want that point there. That just becomes inefficient and it can become counteractive to the band. So we want to make sure we move those points near the band. If the band splits too far, then, you know, we might have to go through and actually create multiple points or adjust the drape. Let me go ahead and answer a question here. A question is, for the junior engineers, could you advise on how most end panels are unrestrained and fire code requirements dictate a higher CG from the bottom? Yeah, so if and Michael, I don't right now, I want to, we're limited on time, so I can talk to you about the definition of unrestrained versus restrained. I think that's more of a in-depth conversation, but in general, depending on what the end bay condition is, if it's unrestrained, then you typically have to have more fire rating or safety for the tendons. And so the end span would become, instead of 1 inch for the CG, we might actually use 1.75 inches per code for the CGS. So that could be adjusted. If we assume that these end panels are unrestrained, right now you'll notice if we go ahead and turn on the CG, if I go to tendon editor under CG, these are all shown as 1. So I say, well, I want to assume that that's unrestrained. We have some argument to make for that case. I could just come in and say these all need to be 1.75 and just simply window select those cables and window select these cables. So that's how it would be done or handled just from a modeling standpoint. Okay, all right, you're welcome, thank you. Another question, why do you have only 2 strands as distributed tendons? Is it because it's an example? Usually we have about 5 tendons at 5 feet on center. It's really just dependent on the requirement. It's just part of the design. So to start, there's certain code requirements that we have for design of PT slabs. We know we need a minimum amount of pre-compression. That's the easiest thing to target when we're actually modeling post-tensioning into this type of a environment. So I don't quite yet know if I need more density of cables or more cables per foot, because it's really a matter of whether we're meeting enough load balancing, whether we have enough pre-compression, and also we have to also meet the requirement for the allowable stress. So once we analyze and design this slab, we might actually find that you know, if you look at a bending moment on this strip, you might have a bending moment here and then a larger bending moment here. We'll say, just for example, this might be 300 kip feet and 100 and 100 in these spans. So this end span that has a larger bending moment is going to produce more tension stress at the bottom fiber. So when we go through and we design the slab and we see that, oh, this, you know, every strip on this end bay is overstressed, then we might actually come in and say, well, we actually need to add a tendon in between each existing tendon. So this has double the number of tendons on both ends. We don't really need that requirement here. It may not be as efficient to add them throughout the entire length, so we might use add tendons. It's really dependent on how much load, what the you know moments are, what the outcome is in terms of the analysis. But for starters, when we're entering the cables, we have to start with something. So we're trying to just meet minimum pre-compression for now. Okay, let's go ahead and adjust, see if we can get through these cables. Let me model. I'm gonna go ahead and move these points over. I'll just move this over. I'll use this as another, this will become another primary tendon that I'm manipulating now. Let me save the file. I'm gonna right click, I'm gonna insert a point right there and just move it over. So this is a new high point. If you double click on this new tendon, the geometry in this area changes. You have a cantilever on the left and a cantilever on the right. So I need to make sure that this looks appropriate. We're going to change this end span here to cantilever down, and this starts to become, you know, a very, very short cantilever, so that hump will actually kind of flatten down to the CG as you move down. Whether or not you want to get that detailed with the layout, you might say, well, just adjust that and make it come out straight of the CG of the slab, right? So that's one thing we can do. We could also adjust this. This is going to be a straight profile. This is only 10 feet. We may not need a lot of uplift or load balancing there. So I'll just straighten that out. We have another long span and then another cantilever down. This is a legitimate cantilever on this side. So this will be a cantilever down shape to the CG of the slab. Whether you use a cantilever down or a straight shape or a cantilever up, they all produce very, very similar results. You'll get a slight difference between a cantilever down and cantilever up just based on the induced moment from that cable. But this will be the new primary cable. I'll take that and I'll go ahead and I'll replicate that down. At 4-foot spacing, we'll do 6 copies of that. And I see that there's another question. I'll address that here in just a moment. Slide these points over while we're at it. I'll come back and fix these other tendons near the opening. You know, here we could probably just use one point. It's a straight shape between these 2 points that I'm adjusting, so it's not going to be it's not going to be harmful to the design. So this will be the layout of those cables. Let's go ahead and address. There's a question. When we run banded tendons through a column, we specify the number of tendons banded together in one area. Then we run another band going through another column line. Let's say 25 banded tendons together. The way you're showing it, do we have to input every tendon manually like this? Can we just specify a group banded together and just draw one line through a column line? Yeah, you could. I mentioned earlier that you could do a banded arrangement. Again, the program is flexible in terms of how you model the cables, as long as it represents the location that you want cables present in, and to you know, be able to represent, let's say, load balancing in that area and be counteractive to the gravity loads. You could represent it really any way you want. You could do banded. I could split this up into groups of 10 cables every 10 feet. Here I'm just showing what's, I guess, most common with modeling in the software. So let's go back to this cable here. We're going to delete out this point. Oops, I think I inserted a point there. Delete those points. I'll take this point and just run it back to the face of the column, or the face of the opening rather. Do the same thing here. Okay, and then I'm going to take this and copy this down again twice. So I'll go back and we'll take 2 tendons. We're going to copy those. And now I'm going to delete from the opposite side. So we'll delete out those points, take that point and move it back. Do the same here. I'm just right-clicking to engage that set of tools to delete and insert the points. Okay, those are my tendons at openings. And then the last part will be up in this area here. So we'll go ahead and copy that up. Again, I don't have to copy. I could just draw a brand new tendon. The reason I copy is just easier for me to edit the cable than anything. So remember, this right now is a reverse parabola. It actually is copied from this span, which is a RP shape. So we're going to go back and modify that to cantilever down, and then copy that tendon up just a couple of times. And we could always bring that tendon. This is the one tendon that is not spaced at 4 feet. So the reason I like to keep the spacing consistent, it makes it easier to translate the results into a drawing. If I have varying spacing, which sometimes you may, it's just harder to take that and to synthesize it maybe into a, different zones of force per width, force per foot, or force per meter of representation of the uniform cables in a drawing. So I know everything is consistent. One thing to note, this area we're going to say is RC, so that's important to note. So now we're ready to go through and we're going to mesh the slab. Okay, we're going to use just the default combinations. The main goal really here is to show how do we go through the checks for the design of the PT slab. And that primarily is a function of the serviceability combinations. The strength combinations are also affected obviously by the post-tensioning, but until you meet, for example, deflection, let's say pre-compression, stress control, and also balanced loading, the strength outcome will fluctuate. You may have more tendons that you need to add to a certain location. That means you have more capacity, and your reinforcement may be lessened for strength control. So for the kind of the ultimate level design. So let's go through and design those combinations. Okay, and the second step will be, we're going to generate our strips, and we're going to design the design cuts for the slab. And this design really goes through and it just processes all of the design strips for a solution in terms of serviceability and for strength checks. So we'll select yes to that. Now I want to turn off the elements, the shell elements, so I'll go over here to analysis and turn off this from the visibility tab. And I also may want to turn off the tendons just for starters. So I'll turn the tendons off. First thing I want to check is pre-compression. There's two options for pre-compression. If you go to the design sections, under stresses, there's pre-compression FEM and pre-compression number of tendons. Originally, until I think version 2017, we only had FEM. We essentially took the design cut. If you take this cut right there, there's a cut, has some area of the, I'll say area of the cut, area of the concrete, and we take the axial force that's integrated as a resultant force. Let's say this is called N. That force at the CG of the cut due to the in-plane action is used, and we take N over A sub C to get the FEM result. That could be a little bit tricky because if the slab and the layout of the walls and the supports was in such a condition where you actually started to develop in-plane restraint, then you would see a huge drop off in pre-compression. And some users would fight that. They would say, well, we know we're going to detail the slab to release the slab and allow it to shorten, or we might have pore strips or a combination of those two things, but the program doesn't really simulate that. So I'm getting this drop of pre-compression that's kind of diverting into walls and supports. So one way to alleviate that would be to just say, well, assume that your slab is allowed to shorten. And if we assume that it's allowed to shorten per that detailing and that evaluation, then we can just use pre-compression number of tendons. Pre-compression number of tendons just says, take the total force of tendons cutting a section and divide it by that same area. In some cases, both of these options really might be used to evaluate a slab, because if you had a section cut here and then another one right there, and you have tendons cutting through there, let's say you have 1, 2, 3, 4, and then this tendon is really close to the edge, and here you only have 1, 2, and 3, and these cuts are of identical length. Well, you're going to have a high pre-compression here, maybe it's 160, and then because this only has 3 tendons, you're going to have maybe 120. The control that code checks this is set under display. That's set to 125 right now. This one would say no good, this one would say okay. And that's more of a mechanical check. In reality, if you go to FEM, that distribution of stress would be more uniform, and both of them, this might jump down to 145 and 145. So you just have to watch out what's going on with the tendons and the distribution of the cuts when you're using number of tendons. But if we go and check this in our model, you can see, notice that by default max min are shown. You can control that from floor design under numerical display. And these are the pre-compression values that were produced. So let me change the decimal to 1, and I can also control the font height. Let's change that to 4. So we would go through and we would make sure that our pre-compression is sufficient. And you can see the difference. If I look at this internal strip near these walls, this is hovering around just over 320, maybe to 300, a little less. If I change that to FEM, now that drops. So some of that force in these tendons might be diverted into, let's say, the wall elements. But it's still sufficient. You can see right here, there's some strange result there where I'd have to go through and check out why that's happening. But that might be more of an anomaly in terms of the actual solution for that node in the general solution. Up at the top, I'm going to go back to number of tendons. At the top, you can see these are all flagged as 0. This is an RC section of the slab. There are no tendons that actually cut that location, so those get flagged as 0. The code check says, oh, those are no good, but in reality, this is really an RC location, so we're going to ignore that in this case. We would check the pre-compression in both directions. I'll go to this direction also, and you can see there's a little bit of a drop here. So and by the way, these tendons, I'm going to point to these. So this tendon here and this tendon here are the primary banded tendons for, let's say, this cut right there. But you also have a little bit of force from this cable that intersects it at some very shallow angle. So any tendon that, that intersects that section, there is a initialization range that where if the tendon, I think, is less than 30 degrees, it would not consider the cable. I'd have to go back and check that. But some of these cables may be considered based on their orientation relative to these design cuts. But here you can see we're a little bit low on this line. So we might add another tendon here. I don't know how many tendons are there now. There's 6 times 2, so we might change this one to 7, have a total of 13, reanalyze, redesign to update that location. The same thing is going on here, and there's a little drop there. The second thing we might want to check after we solve the pre-compression would be the stresses. And if we go back and say, okay, let's go back to the X direction. I think it's a little easier to see that. Bottom stress. So The bottom stress, let me look at the moments. These stresses look a little strange. Okay, so there's the issue. That actually reared its head in the RC model. No wonder that was not working. Let me do one thing here. One moment. See if I can fix this. Okay. I'm actually going to move this one up too. I was having the same issue with the RC model, which was causing, it was just causing the overall range of values to be completely skewed towards that high value, so you couldn't see any of the other graphs because of it. Let's see the outcome here. Yeah, the same thing's happening on this side, so let me go back and readjust. I'm going to pull that off of this wall. I'm going to pull that off this wall, and then what I'm going to do is if I'm going to take these splitters here and move those to the outside again. So let's create a splitter here. Another thing we could do is use a wall boundary tool in the program, but I'll just do it through use of the splitters for sake of time. I have probably another 10 minutes or so. I know I've gone over time, so I appreciate everyone sticking with me that's still here. All right, let's go back and design the cuts again, see if that resolves that issue. It's just an integration problem with the nodes and crossing those walls. So let's let me try one more thing before we give up here for today. I'm going to select this wall. Actually, let me go to my wall design just to isolate the walls. And what I'll do is create a boundary. So I'm going to say these walls, if we go to floor design, dynamic editor, walls, we can say these walls here, I want those to be a boundary for Y direction support lines. So we're going to change these. That means the program will not cut, should not cut the sections into those walls. Once I've done that, we'll generate the cuts again. Come back to this direction. Still have some issue there. I'm going to try this one more time before I actually remove those two support lines, just so we can get some results for the X direction. Okay, let's go on. Let me do that. Design the sections again. All right, so back to this direction, X direction here. We have our bending moments. This is for service total, and you can see the bending moments there. If we go back and look at the stresses, we have some stress issues in some of these spans. Again, these moments or stresses look a little bit strange, obviously high, but ultimately we would want to go through and resolve any stress problems in the slab. Now, how do we resolve those? We would either have to manually go through, add post-tensioning, adjust CG, adjust cables. This is not a great example because these results just look a little bogus to begin with, but we would go through and use what's called the tendon optimizer to resolve some of those issues. And when we go into the tendon optimizer, that allows us to utilize kind of, it's a program, it's a sub routine that is similar to the ADAPT recycler if you've ever used ADAPT PTRC. And what I can do, I want to show you that optimizer here before we conclude today's training. I'm going to go and just generate a model using the wizard. Again, because of that result issue, let's just use the floor wizard. I'll do 3 spans, both directions. We'll do 30-foot bay, both directions. I'll bump up the loading here again to hopefully create an issue here with the stresses. So we have our slab. Let me save this. Same process here. The tendons are just modeled automatically through that wizard. Okay, we can also generate the strips automatically, so we'll generate those cuts in the slab. Let me go back into my default display, and then I'm going to design the cuts. So the goal is to get to a point where we could utilize that tendon optimizer. Okay, if we go back to the stress check, we're working with service total condition that would produce potentially the maximum stress issue. So we'll go back here to design cuts, stresses, bottom stress. And you can see there's over stresses on these two end bays. And the allowable stress here is 379. I think the default material is 4,000. 6 square root of F prime C, which is set up under the criteria allowable stresses. That's the default for two-way slab. If we go back and numerically just turn on the values here, we can see we're at around 449, allowable is 379. So rather than going and guessing what tendons need to be added maybe to these end bays, this is symmetric, so we could do one side and then copy tendons over if we needed. We're going to use the optimizer, and I'll optimize this interior bay. We're going to go to tendon, optimizer. In the optimizer, I'm going to set, actually let me exit that for a moment. I need to show the tendons. So we want to set up our different settings here for optimization. So we're going to say what will happen is the program will develop essentially 3 virtual cuts, A, B, and C, within the tributary that we want to optimize, and that's based on the selection of tendons. So for this selection of tendons, what we'll do is we'll say we want to optimize the balance loading based on self-weight and dead load. The 2 end cuts, the virtual cuts A and C, are going to be 2% of the span length. That gets us close to the face of support. We can produce the result for stress either by ratio, factor, or the actual stress. This is just how it's presented. We'll target a pre-compression range and a load balancing range, and the allowable stresses will be a function of the criteria. Two-way slab, 6 square root of F prime C. So now what I can do is actually select the tendons that I want to optimize. So I'm going to select these tendons here, which are essentially tributary to this strip that produces that stress result. And what you'll notice is the program will kind of itemize all the tendons that are currently there. It shows tendons 1 through 13. Under the optimizer, the current force, if you sum up that force, is 351. And that actually meets the pre-compression range, and that shows the higher, the lower and the upper bound forces needed for this pre-compression target, as well as load balancing. However, the stress is exceeded. You can see there's a top stress that doesn't work based on the current result somewhere over here, and there's a bottom stress that doesn't work. That's the one in that pink zone there. And if we were to increase the tendon force from 351 to 588, then the stresses are relieved. You can see there's the new updated values. We say, okay, great. We want to update the model to reflect this delta in this tributary. So we'll go to apply to model. I could distribute this total change, which is 237 over 13 strands. It's really 8.78 strands. Or I could say I just add it to a single tendon, or I want to create new tendons. I'm going to create add tendons. We're going to start the add tendons between existing tendons 1 and 2 right here on the bottom end of this range. The total number of tendons I want to create is 12. I want to put a new tendon in between all existing tendons, and we're going to add these from point A. There's virtual cut A. I'll say add partial tendons from A with a tail of 30% to the slab edge. And if I apply that, you'll see the program will actually draw in those add tendons into the slab. I could have actually selected this entire bay as a range. The program adds these. If we double click on the cable, you can see it's actually a decimal value. It's 0.73, so we may want to adjust that, but this is the shape of the cable. Once you add the tendons, then you could reanalyze to get the updated results through the strip results. So that's an example of how we would go about optimizing the cables. Once we've once we've optimized all of our cables, we have a satisfactory design for post-tensioning, then we would get into the design of the reinforcement, maybe the punching shear checks, and just downstream the final final design from a gravity standpoint. And what I'll do is actually I'm going to create a second webinar. Today we're out of time, but I'll create a second webinar that covers the remainder of the material, which will again be strength design, punching shear design, and being able to take that for completion and producing a reinforcement plan. So we'll go ahead and I'll stop there for today and reserve the next 5 to 10 minutes. If there are any questions, I'd be happy to answer questions for that. What I'll do, I know all of you that have signed up for this webinar. For the next webinar, I'll actually create that, send you the invitation, give you a day or so to determine if you want to join that one, and then I'll just open that up to the public for anyone who wants to join. There is a limitation on enrollment. So, all right. So any questions? I'd be happy to answer at this time. And you can, if you do have a question, feel free to just type that into the chat box. Okay, I'll go into auctioneer mode, going once and going twice. Any questions? I'll wait a little bit longer till everything is sold here. So what are the biggest changes in the current version? So good question. If we relate it back to version 18, Brian, are you talking about between version 18 and 19, or are you talking about between version 2019.1 and 2019.2? Yeah, 18 and 19. Good question. I can't remember all the changes off the top of my head. I know there were a lot of changes to the shop drawing module. So if you go into this module, there was the option to produce, felt reinforcement or loss calculations, and also produce these reports for the losses. There's also been P delta was introduced. That's another big change between the two versions. If you go to the load combinations, you can actually run a model for P delta, so second order effects. Because of that, we also made improvements to how the drift is reported. So when you introduce, even without P delta, there's options now, new changes to drift. You can see there's some new added amplification options here that relate back to second to first order effects. The same thing under actions for moments. If you look at the amplification for moment due to P delta, there are new reporting options for drift under analysis data. So there's this drift report that's a really nice report. Aside from that, what I can do, Brian, is I'll send you the release notes that kind of summarizes the new changes. Those are the only ones that come to the top of my head, but I know there are a few more. I just can't recall from memory at this point. So I'll send that over to you. Okay, other questions? All right, we'll go ahead and stop there. Remember, this will be placed on youtube.com/adapt support, and then I will make sure to send all of you the let's say part 2 of this webinar, and we'll conduct that. It'll likely be next Friday. I have another webinar scheduled for next Thursday. So I'll make sure to get all of you that invitation. And then if you have any questions outside of the meeting, again, you can always contact us at support@adaptsoft.com. Thanks again.